Okay, let's do an example where we think about the error bound for a Taylor polynomial. Let's consider the function e to the x cosine x. And we're going to find a bound for the error when we're approximating f at x equals 0.5 by the second Taylor polynomial evaluated at x equals 0.5, where the Taylor polynomial is expanded about x sub 0 equals 0. Just as a reminder, the second Taylor polynomial and its remainder are shown here. So for some function f of x, if I expand about some value x naught or x sub 0, I have f evaluated at x naught plus f prime at x naught times x minus x naught plus f double prime at x naught over 2 times x minus x naught squared. And then I have a remainder term here. So this expression up until the remainder term is the second Taylor polynomial. And this last term here, as I'm going to call R2, this is my remainder term. Now, this remainder term pretty much tells us that if I just approximated my function f of x with this second degree polynomial, and I wasn't considering this really right now, if I just stopped there, the remainder term captures how far off this quadratic polynomial is from this function f of x. It sort of captures like all the other terms. There really would be infinitely many terms, but we have this existence condition that all of those other terms can be encapsulated in this term. There exists some value c where this term captures all of those other terms. Now, the issue is that we don't know what this value c is. All we know is it's between where we expand the Taylor polynomial about and where we evaluate it. So all we know is that c of x is between x and x sub 0. In our case, x, where we evaluate, is 0.5. And x sub 0, where we've expanded the polynomial, is 0. So c is going to be between 0 and 0.5. So that's really all we know at this stage. Now, the reason we would bound an error term is because we want to know how bad, like the worst case scenario, how bad could this approximation be? And we want to give sort of like an estimate for the worst case scenario because we don't really know much else about this term. So we need to know like how big it could possibly be. So we're going to consider the error. So on 0 to 0.5, we want to bound this error f of x minus p2 of x. Now p2 again is this full expression here, and if I subtract all of this over to the left, on the left I have f of x minus p2 of x, and on the right, this all has been subtracted over, I'm just left with r2. So this really is r2 x, which in this case we know looks like the absolute value of f triple prime evaluated at some point c of x over 3 factorial. In our case, x sub 0 is 0, so this would be x cubed. So now we need to compute this quantity using our function f of x. You can check that, sorry, I lost my pen there for a second. You can check that f prime of x is equal to e to the x times cosine x minus sine x. F double prime of x is equal to e to the negative 2 e to the x times sine x, and f triple prime of x is equal to negative 2 e to the x times sine x plus cosine x. This is the expression we are going to place in here. And we want to bound this entire term in absolute value over the interval 0 to 0.5. Okay, so let's do that. So we are going to compute. We've got right, R2 of x now looks like negative 2e to the c of x times sine of c of x plus cosine of c of x all over 3 factorial times x cubed. Now notice here I had this expression for f triple prime, and in the remainder term, I am evaluating that expression at c of x. So wherever I see an x, I'm going to put c of x. All right, in absolute value, this negative doesn't really do much. So I could drop the negative, and then 2 divided by 3 factorial. 3 factorial is 3 times 2 times 1. So the 2's cancel, and I get 1/3. So really, I've got e to the c of x times sine c of x plus cosine c of x all over 3 times x cubed. And I want to bound this on the interval 0 to 0.5. Now, this portion of our expression, I can bound pretty easily from on 0 to 0.5. This is an increasing function, so the maximum is going to be when x is at the right endpoint, 0.5. So we could also think about this as being, really, I want to think about this. The max, this expression is less than its maximum, so the max on this interval of this expression. I'm going to write this out in a couple steps so you can see why I'm doing what I'm about to do. Over 3 x cubed. Okay. You could just go straight into trying to bound this. That's totally fine. I'm going to split this up into a couple pieces. I'm going to say that the max of this product of this term and this term is less than or equal to the maximum of each piece in the product. So the max of, I'll let this part be the 1/3 x cubed part times the max of, over this interval, of e to the c of x times sine. Okay, now why do I know that? Well, and I know it has to be less than or equal to, because if I were just computing the max of this over the interval 0, 0.5, I would have to use like the same, like I'd be evaluating this at one value of x. When I split it up, the max of this and the max of this may occur at different x values. So if you think about this as like, maybe I'll draw a little picture. If this is my function, well, maybe I'll do this. If there's my function f of x, and let's say there's my function g of x, say. Like maybe I'll call it, here's y1, here's y2, I'll say that. Then the max of y2 happens over here, and the max of y1 happens over here. And if I took the product, I would get something different. So I'm going to multiply this by the maximum I could possibly get here and the maximum I could possibly get here. This is going to be less than or equal to the product of those things. Okay. So, like I said, since x cubed is increasing on this interval on 0 to 0.5, we know that the max on this interval of 1/3 x cubed occurs when x equals the endpoint. This function looks like, let me draw it like this. Here's x, here's y. X cubed looks like this, something like that. And the interval 0 to 0.5 is somewhere here, and this is an increasing function. This is going to be 1/3 times 0.5 cubed is 1/3 times, hold on, let me check this value. 0.1250. So that's just for this portion. Is like the biggest that that portion could be. And let's also check the largest that this portion could be. I should also note that here I know I gave a reason why I know this. I know that x cubed is increasing, so I know the max occurs there. That's fine. But if you didn't do that, or if you weren't sure, you could also have used the extreme value theorem. Okay, and found the critical points and endpoints and tested each point, each value there. You could have done that. Either one is okay with me. Now we want to switch gears and figure out what this bound should be. So to do this, I'm going to define this portion as its own function, and just because I want to like talk about it on its own. You don't have to do this, but it helps me think about what I'm doing a little bit easier. So let's let g of x be e to the x times sine of x plus cosine x. So I'm thinking about this, but instead of c, I'm using x. This is also okay. I want to bound this an absolute value. And I want to apply the extreme value theorem. So I'm going to note, oops, here we go. I'm going to note that g is actually differentiable on this interval. So it's in C1, which means I can use the extreme value theorem, and it tells me, so the max on this interval and g of x, an absolute value, occurs at really at either at one of the endpoints or at a critical point. Okay, so I need to just test the endpoints and critical points. So let's first find the critical points. We have that g prime of x is, you can check that it's 2e to the x cosine x. And the critical points here, the critical point of g of x occur when when cosine is 0. And if we think about the unit circle, cosine of x is 0 here and here. This is at pi over 2, and then 3 pi over 2. We can go back around. So there's really odd multiples of pi over 2. X equals, let's say like 2k plus 1 pi over 2, where k is an integer. Really, the first time, or the smallest x value where this occurs would be pi over 2, which is not in the interval. There are no critical points in this interval 0 to 0.5, so we check the endpoints. G of 0 is e to the 0 times sine of 0 plus cosine 0. That's 1 times 0 plus 1, so that's 1. And g of 0.5, you would just plug 0.5 in there, use a calculator, you would get approximately 2.2373. Oh, sorry, didn't mean to do that. Then finally, remember we're using this value way back over here. Oops, sorry, not right there. Here, we're trying to bound the error term, and we say that we got that the error is less than or equal to this. Maybe I should just like copy this over so that it's all on one screen. Go down here, paste it. Oh, I pasted it way up here. Okay, this is fine. Let me get rid of some stuff. It's not as pretty as I'd like it to be. Okay, sorry, that was a little messy. What I wanted to have here is that the error, or the remainder in absolute values, bounded by this expression, which we already saw earlier, which is less than or equal to, the max of this is 1/3, I forgot now, 0. What was it? It was like 125, sorry, 1250 times the maximum of this quantity was 2.2373, and if you do this computation, it's approximately equal to 0.0932. And this is now our bound on the error in P2 over the interval 0 to 0.5. Okay, that's it for this example. I hope you found it helpful. Let me know if you have any questions.